Hello everyone, I'm Wang from Baidu Research. In this talk, I will report our recent results on the measurement error mitigation via Truncated Neumann series. This is a joint work with my colleagues Readout and Chen. You can find the archive version here. This talk is composed of two parts. In the first part, we formally define the measurement error mitigation task and present literature review. We summarize some known results. In the second part, we introduce in detail the proposed methods via Truncated Neumann series. The key idea is to approximate the metrics using Truncated Neumann series. Okay, let's go. So, consider an ideal quantum computing of the following form. It initializes n qubits, evolves through a quantum circuit consisting of elementary gates, and terminates with a product measurement. However, measurements on near-term quantum processors are inevitably subject to hardware imperfections, leading to the so-called readout errors. The readout error will result in a noisy output probability distribution rather than the ideal one, and thus yielding incorrect computation results. This is what we call the quantum computing with noisy measurement. For example, the celebrated IBM Q system and Google ThinkMore are both suffering from terrible readout errors, ranging from 3% to 16%. Needless to say, mitigating such noise is crucial to better explore and enhance the power of near-term quantum devices. We first set up the noise model. Experimental and theoretical works have demonstrated that noisy measurement can be well understood classically as ideal measurement followed by classical perturbation. That is to say, you can think of as that the ideal probability distribution is generated. However, it is perturbed unavoidably, resulting in a noisy probability distribution. The classical perturbation is modeled by a closed stochastic matrix A of size 2 to power n. That is, the noisy distribution is obtained by left multiplying the ideal probability with A. In general, A can be learned via the so-called measurement calibration procedure, so we may assume it's non-operial. Within this classical noise model, the problem is very clear now. Given the stochastic matrix A, which can be learned via calibration, and the noisy probability distribution P noisy, which can be obtained by running the noisy quantum circuit, how can we estimate the ideal probability distribution P ideal? There are many methods dealing with this problem up to now. The most well-known one is the so-called matrix inversion method. We simply calculate the inverse of the matrix A and left multiply the noisy probability distribution. The resulting vector will be used to approximate the ideal probability distribution. However, this method has several limitations. For example, A may not have an inverse at all. It is hard to compute the inverse. What's worse, even if we have the inverse, the resulting distribution might not be physical. It may have some negative elements. To deal with these issues, the least square and the iterative Bayesian unfolding methods are proposed. Very recently, Bravery et al. Proposed a novel method that cancels errors using quasi-probability decomposition method. Of course, there are many more interesting methods that I do not mention here. All these works imply that the error mitigation is an active research topic. In the second part, we introduce a new method to mitigate Neumann noise. The key idea is to approximate the inverse of the stochastic matrix via truncated Neumann series. Let's first formally define the computation task. We focused on the task of computing the expectation value. This task has 3 steps. First, it generates a quantum state row via unitary evolution. Then it measures the state, which suffers from readout errors. Using the measured outcomes, it computes the expectation value trace or row. I emphasize that this kind of task is the essential ingredient of many well-known readout algorithms, such as variational quantum eigensolver and the QAOA. Without a loss of generality, we assume the observable O is diagonal in the computational basis. So ideally, trace O row can be computed by multiplying the elements of row of O and the P ideal, and summing up all the elements. However, practically, the expectation value will be corrupted by the noise matrix A here, and does not equal to the trace O row in general. So ideally, we want to obtain trace O row, but practically we can only obtain the noisy version. This is the gap. In the following, we will apply the Neumann series to deal with the annoying noise matrix A here. But what is Neumann series? Mathematically, the Neumann series says that when a square matrix A satisfies certain constraint, more precisely, its readiness spectral readiness is strictly less than 1, then its inverse can be expressed as the sum of an infinite number of terms of different orders. Let's rewrite the first k terms. Then we can establish an equivalence between the inverse and the linear combination of different orders of A here, with carefully chosen coefficients. This is very good. This is to say, we can approximate the inverse, which is hard to compute, by many different orders of the original matrix A. Now let's see how we can apply Neumann series to mitigate Neumann error. First of all, notice that the annoying matrix A can be cancelled by left multiplying its inverse A in -1. We then expand the inverse via the truncated Neumann series with tailing terms which are negligible. Rewriting the equation, we can see that the ideal value trace O row can be expressed as a linear combination of expectations values of different orders from order 1 to order k+1. Thus, we can compute each expectation value of given order individually and then sum up later according to some carefully chosen coefficients. Roughly speaking, the method is divided into 2 steps. First, we apply the matrix inverse and we use Neumann series, truncated Neumann series to replace the inverse. Then we expand the ideal value as a linear compilation of expectation values of different orders. But how to compute the expectation value of a given order? So notice that the expectation value of order k is defined as this. When k equal to 1, we recover the original noisy expectation value. Effectively or intuitively, the expectation value of order k can be obtained by a noisy measurement device whose noise matrix is a to power k. The key observation is that a to power k can be effectively simulated via k sequential uses of the original measurement device. So you can see here, if we use the device once, we just obtain a, which is the original error matrix. But if we use the device twice sequentially, then we obtain a square, and so on. This is very cool. It gives us a feasible way to estimate expectations of different orders using just the original noisy measurement device. Another problem is to bound the truncation error analytically. As we studied previously, the ideal expectation value trace overall can be expressed as a linear combination of expectation values of different orders with a tail term that we need to bound. Luckily, we show that the absolute difference between trace overall and the linear combination is upbounded by a quantity that decays exponentially in terms of the truncated number k. The noise resistance of A quantifies how the noise distorts the measurement outcomes in the worst case, and it determines the number of truncated numbers required to achieve the desired position. Notice that 1 minus half cap is exactly the minimal diagonal element of A. This is a very interesting quantity. Okay, putting everything together, the error mitigation method goes as follows. First of all, we compute k, which is the optimal number of truncated Neumann series terms. It is determined by the desired position epsilon and the noise resistance of the noisy measurement device. Then, for each small k ranging from 0 to big K, we compute the expectation of order k by using the measurement device k plus 1 times sequentially. At last, we linearly combine these noisy expectation values according to the coefficients. Our theoretical analysis previously guaranteed that the output E star approximates trace overall within position epsilon. As one might see, the truncated number k affects the approximation position greatly. In this figure, we plot the optimal number k as a function of the noise resistance k, where the position parameter is fixed to 0.01. From this figure, we can see that k is less than 10 whenever the noise resistance satisfies the condition that it is smaller than 0.67. Equivalently, this means that the minimal diagonal element of A is larger than 0.7 5.67. This is a very reasonable requirement for near-term quantum devices. To summarize, the truncated Neumann series terms would be small, say it will be less than term whenever the noise matrix is moderate, in the sense that it is below a certain threshold, say the chi is less than 0.657. In the extreme case, where the minimal diagonal element of A approaches 1/2, in this case, the measurement would be very, very noisy. Then the optimal truncated number should be infinity. We apply this method to the following example to show its performance. The input state phi is the maximally coherent state of n qubits, and the observable O is the tensor product of Pauli Z operators. Obviously, the ideal probability distribution here is a uniform distribution, and thus the ideal expectation value should be 0. We then randomly generate a noise matrix A whose noise resistance is 0.657, falling into the moderate region. That is to say, around the turn repetitions is enough to approximate the inverse. We repeatedly produce noisy and mitigation expectation values for a total number of 1,000 times, and all the data is scattered in the left figure here. It is easy to see that the noisy measurement introduces a bias around -0.007 to the ideal expectation value, which is identified by the blue dots. On the other hand, the mitigated expectation values, red dots, distributed evenly around the ideal value 0. The right figure shows that the noisy and mitigation expectation values obtained via the left procedure as a function of the number of qubits. The entire experiment for each n was repeated 1,000 times to estimate the error bars. One can see that the crosstalk error in the noisy measurement device severely affects the estimated value, while our error mitigation method is insensitive to this kind of error, since for all number of qubits, our mitigated value is approximates the ideal value 0. Now let's briefly summarize this work. We have introduced a scalable method to mitigate measurement errors when computing expectation values in near-term quantum devices. The key idea is to approximate the inverse of the stochastic matrix using truncated Neumann series. We emphasize that the proposed method works for all classical noisy models, since we do not assume any noise structure a priori. What's more, we do not require the full knowledge of measurement calibration, but only the noise resistance parameter, which might be estimated efficiently. What's more, the incurred overhead in terms of state copies and measurement is independent of the system size, as long as the noise resistance of the noisy measurement device is moderate. We believe that this method will be useful for experimental measurement error mitigation in near-term quantum devices. Okay, that's it all for this talk. Thank you for your attention. See you.